Okay, you're interested in flow fields. Well, take a look at your screen. You'll be able to make all these demos on the screen and more by the end of the video. I'll cover anything and everything about flow fields, from vectors, to particles, to colors, to modifications and optimizations you can make with them. Alright, let me get right into it. So, what is a flow field? A flow field is a description of how objects move through space. Here we see a field of vectors and a particle moving through it. The vector underneath the particle describes the particle's movement. That's what we could call a flow field. So, how do we make this? We'll have to create a system where we have a field of vectors and particles atop these vectors, such that these particles' movements are skewed based on which vector they are top of. Then, we could remove all the vectors and make modifications to this, such as changing color or anything to make it look more interesting. I'll be using raylib with C++ as I have in my previous two videos, and then I'll have all the resources in the description, such as the code that was written in the video, some other stuff like the makefile to compile the code, and then resources to learn Perlin noise, which is an algorithm that's going to be used throughout the video. Okay, so here are the files we're going to need. We'll need our main file, which we're going to call flow, and then we're going to have to implement three more classes: our config class, our particle class, and our RealVector class. Alright, let's get right into it. Alright, so we're going to want to start with implementing our main class. So this will be called flow. We'll do our include, so include raylib and IOStream, then initialize our window. While our window shouldn't close, this is where our drawing logic goes. And then finally, close window is a function that will wrap up everything on window close. Alright, we'll come back to this file later for a lot of the main logic, but for now this is all we'll need. Okay, let's check out this window that we just created. So if we compile our code and then run it, we should be able to see a blank screen, just this window. Alright, let's keep moving. Okay, next let's implement our RealVector header file. Each vector is going to need an x and y coordinate and constructors to set those, and some key essential functions for a vector are going to be vector addition, vector subtraction, constant multiplication on a vector, the ability to limit the magnitude of a vector to a certain range, and getting the current magnitude and angle of a vector. Okay, let's go ahead and implement those. Alright, now let's implement our RealVector class. So first things first, we're going to need our includes, our RealVector header file, and then our math library. We'll have our constructor, which just sets our x and y's, and then we have our three crucial vector functions: vector addition, vector subtraction, and constant multiplication on a vector. All pretty self-explanatory implementations. Next we have the vector limit function, which will limit the magnitude of a vector to a certain range. We have the parameters called min speed and max speed, since they'll be utilized specifically for limiting the speed of a particle in this video. Now, we will get the current magnitude of the vector, and if that magnitude is 0, we will return the current vector, otherwise we'll keep going. Now the getMagnitude function is a function written in this file, it just hasn't been written yet. Now, if magnitude is greater than max speed, then we'll multiply our current vector by max speed over the magnitude, and otherwise if the magnitude is less than the min speed, we'll multiply the current vector by min speed over the magnitude, and set these to res. Now, at the end of this we'll return res. Now let me show a quick visual example of how this works. Okay, here is a visual of our vector exceeding our max length. So we divide it by its magnitude, turning it into a unit vector, and then multiply it by the maximum length, turning its magnitude to the maximum length. This is essentially how our limit function works. Okay, now we have our getMagnitude function, which is just a distance formula, and then our angular function, which is just some trigonometry. And that sums up our RealVector class. Okay, let's keep moving. Alright, next thing we got to implement is our configuration file. So this is our config header, and this file is going to store a bunch of variables that we'll need to reuse or reference in our flow file. So first things first, our includes. We include raylib, standard vector, and our RealVector header file. Then our screen variables, these are defines. So our width and height of our screen, scale is going to define the dimensions of a grid cell on our screen, then rows and columns, which are based on height, width, and scale. Next we have our board. So the idea is we're going to have a giant grid, and this grid is going to have vectors inside it. So each slot in the grid is going to have a vector, and this is going to define our vector field. Then when we throw particles onto this grid and make them move based on the vectors, then this will be a flow field. So this slot is going to store a vector and a starting point, and then we'll make sure that we implement board in our actual class file. This is just the header, remember. Then we have the functions map_to and field function, which are going to be important functions that we want to utilize within our flow file. Okay, that sums up our config header file. Now we're going to implement our configuration class. We have our includes, as always, then we have the initialization of our board, which is a 2D array of slots with enough room for the rows and columns of our grid. Next we have our map_to function, which will take in some value between a minimum and maximum, and linearly put it between a new minimum and new maximum. First off, make sure that that value is actually between minimum and maximum using the clamp function, and then we have this one-liner which implements it for us. Originally I had much more segments of code and a solid explanation, but it ended up being 3 minutes, so I'm cutting it out. Next we have the implementation for our field function, which will take in an x and y position and return the angle of the vector at that x and y position. So right now I'm using a random vector field function to retrieve that angle, but later on I'll be using something called Perlinoise to generate these angles. If you'd like to use that as well, I have the code for the Perlinoise function in my GitHub, which you could find in the description. I also have a video explaining how that code was written up and the concepts of Perlinoise in the description that you could watch. Okay, that sums up our configuration class. Now we're back in our flow file to make some visual changes. So first things first, we have some includes, seeding our random function, and 2 new variables, a multiplier and length. Length is going to be the size of the vectors that we draw. Then we're going to look through our entire grid, and for each grid cell we're going to create a slot with the start point of that slot being the middle of that grid cell, and then set that slot to the grid cell. In our while loop we'll look through our entire grid again, and for each grid cell we'll find the angle of the vector in that grid cell using our field function, and then we can make a vector of size length using the angle that we have and the length variable, and set that vector to the slot in our grid cell. Then if we make the endpoint of where to draw this vector and draw it as a line, we finally get our vector field. If we want to zoom in on this vector field, what we can do is multiply the x and y in our field function by some constant, in this case by a very low value to zoom in. We could also add movement by having some random value and incrementing that value every time in our while loop, and make sure that value is added in our field function to our variables. Another thing we can do to make these vectors look more unique is also give them color based on their angle, for example. I changed the angle to a value between 0 and 255 and set that value to some of the color channels. I also changed our multiplier to make sure that the colors stand out and that we get a cool effect. Alright, well that sums up our changes to our flow class. We'll come back to this after adding some particles. In our configuration header, we'll add some new variables for our particle class that we're going to make. And these are going to be particle radius, particle max speed, particle min speed, and the number of particles we're going to generate. Alright, now getting to our particle header class, we'll have the includes that we'll need in our class definition, our variables and constructors. For each particle we'll need its position, velocity, min speed, and max speed. Then 3 functions for each particle to have is apply force, update, and show. Alright, now let's get to our implementation. Okay, now implementing our particle class, it's actually a lot simpler than you would think it would be. First we have our includes as always, and then our constructors, where we take in the position of the particle, velocity of the particle, minimum speed and maximum speed, and set those to our global variables. We have our update function, which will use the particle's velocity and add it to its current position to simulate movement, and then some checks to make sure that the particle wraps around the screen if it goes too far in one direction. For example, if it goes to the very top of the screen and goes over that, we want it to appear at the bottom of the screen. Then we have the apply force function, which will take in a force and add that to the velocity of our particle, and then make sure that that particle is also limited by its min speed and max speed, so it doesn't go over or under. Then we have our show function, which will draw a circle at the particle's position with the size particle radius and some color. That sums up our particle class, and let's get to using it. We're back in our flow file, and now we're ready to implement particles. As a side note, I have some of these code blocks collapsed, so if you're trying to follow along, make sure to take a look at the line numbers. As for our new includes, all we have is our particle header file, and that's it. Next, we want to create all our particles, so we make an array of particles and loop through the number of particles we want to generate, And for each one of those, we'll make a particle at a random position with a starting velocity of nothing and bounded by min speed and max speed, which is specified in our configuration. Then we append that particle to our array. Now to make the particle show up and move, in our while loop, we'll look through all our particles again, and using the particle's position and the knowledge of the size of each grid cell, we could get the vector that the particle is on top of. Use this vector to apply force to this particle, and update the particle and show the particle onto our screen. And now we have our flow field with all our particles in it. So what are some ways we could alter this flow field now? So for one, we could stabilize the particle movement by not making the vector field underneath it move anymore. So we're commenting out this C variable, which was changing our vector angles every iteration. Then just to see the particles and only the particles, we could comment out the line that draws the actual vectors. And finally, for the most interesting result, we could comment out the line that actually clears our background and get something that looks like this. So back in the particle class, a really easy way to make better looking flow fields is to play around with the colors of the particles. A really easy change we can make is just lowering the transparency of the particles, and we get a vector field or flow field that looks like this. And finally, to switch it up a little bit before I conclude the video, for our field function, if we change this in our configuration class to something else, for me, I'll change it to my Perlin noise implementation, where it will generate an angle using Perlin noise. The flow field will look something like this. Lastly, I'd like to say that I wish I could have put more content into this video, but plans change. I hope you enjoyed and learned something, so I'll leave it off by saying go explore, create, and thanks for watching.